Welcome to this lecture on the diversity of chordates. Today, we are going to explore one of the most fascinating and deadly evolutionary adaptations in the animal kingdom, the biting mechanism in snakes. Imagine a creature with no arms or legs that can instantly subdue fast-moving prey. How does it do this without getting injured? The secret lies in a highly specialized, lightning-fast biomechanical system hidden inside its skull. Let us dive in and uncover the brilliant engineering behind a venomous snake's strike. To begin our journey, let us think about a folding pocket knife. When closed, the sharp blade is safely tucked away inside the handle. A venomous snake, like a viper, uses a very similar, brilliant design. Instead of walking around with long, dangerous teeth permanently sticking out, the snake keeps its fangs folded flat against the roof of its mouth. This prevents accidental cuts and saves space. When the snake decides to strike, a fascinating chain reaction acts just like a spring mechanism, swinging the fangs forward in a fraction of a second to deliver venom before folding them safely away. Now that we understand the folding knife analogy, let us look at the biological engine driving this movement. In zoological terms, this process is driven by something called cranial kinesis. Why does this matter? Well, unlike mammals, which have solid, fused skulls, a snake's skull bones are loosely connected by ligaments. This means the bones can move completely independently of one another. This incredible flexibility is the ultimate survival tool, allowing the snake to manipulate its jaws in ways that would be physically impossible for us, setting the stage for a highly specialized and rapid strike. Building on the idea of cranial kinesis, let us break down the exact sequence of events during a strike. It all starts with the contraction of a specific muscle called the digastric muscle. This muscle pulls a bone at the back of the jaw, known as the quadrate bone, forward. This forward motion creates a domino effect, pushing a chain of bones, specifically the pterygoid and palatine bones. These bones then push against the maxilla, which holds the fang. Because the maxilla is hinged, this push causes it to rotate up to 90 degrees, instantly erecting the hollow fang into a biting position. Having discussed the bone chain reaction, let us now visualize it clearly on screen. Here you are looking at a detailed schematic of a viper's skull in two states: resting with the mouth closed and striking with the mouth open and fang erect. Notice the quadrate bone at the back. Follow the arrows showing the forward movement through the pterygoid bone. Finally, look at the front where the maxilla is located. The red rotational arrow clearly shows how the maxilla pivots, swinging the fang downward and forward. This diagram perfectly captures the elegant mechanical sequence we just described. Now that we have seen the anatomy in action, let us understand how this jaw moves so incredibly fast by looking at it through the lens of physics. The snake's jaw actually operates as a biological lever system. Just like a seesaw or a crowbar, muscles apply force to move a series of connected bones. The placement of the jaw joint acts as the pivot point, and this placement completely determines how the system behaves. By studying this exact bone lever system, scientists and mechanical engineers can even design better, more efficient folding mechanisms for microscopic medical devices and robotics. To measure the efficiency and speed of this biological lever, we use the mathematical formula for mechanical advantage. Conceptually, this formula compares the input side of a lever to the output side. Let us look at the symbols. MA represents the mechanical advantage, which is a unitless ratio telling us if the lever multiplies force or speed. L in is the in lever arm, the physical distance from the jaw joint to where the muscle attaches. L out is the out lever arm, the distance from the jaw joint to the tip of the fang. When the out lever increases relative to the in lever, the mechanical advantage drops, which physically changes the bite from a crushing grip to a lightning-fast strike. Before we move on, let us see this formula in action with a concrete example. Imagine a biologist is studying a gaboon viper. We are given the in-lever distance of 2.0 centimeters and the out-lever distance of 10.0 centimeters. We are asked to calculate the mechanical advantage to see if the jaw is built for force or speed. We choose our formula and substitute the carefully measured values. We divide 2.0 by 10.0. Because both are in centimeters, the units cancel out perfectly. Our final answer is 0.2. This tells us exactly how the viper's jaw is mechanically tuned. So, we have calculated a mechanical advantage of 0.2. This brings us to an important mathematical proof of the snake's evolutionary design. What does this number actually prove? In physics, we established that a mechanical advantage greater than 1 acts like a heavy nutcracker, multiplying force. Conversely, a value less than 1 acts like a swinging golf club, multiplying speed and distance. Since our calculated value of 0.2 is significantly less than 1, we are mathematically setting up the proof that the jaw sacrifices raw biting force in exchange for blindingly fast striking speed. Continuing our logical derivation, let us interpret exactly what that ratio of 0.2 means physically. The mathematical reasoning here is that the output distance is 5 times the input distance. Therefore, for every single centimeter the jaw muscle contracts, the tip of the fang moves 5 times that distance in the exact same amount of time. This mathematically proves that the viper's biting mechanism is an evolutionary masterpiece. It is explicitly designed for extreme speed rather than bone-crushing force, allowing the snake to inject venom before the prey even realizes it has been attacked. Now that we have proven how the fangs deploy so quickly, let us look at the second crucial part of the bite mechanism, injecting the venom. Once the fang is erected, the compressor glandulae muscle wraps tightly around the venom gland and squeezes it. This powerful squeezing action forces the venom through a tiny duct and out the tip of the hollow fang, acting exactly like a biological hypodermic needle. Understanding exactly how this gland is squeezed helps medical professionals design better protective gear for snake handlers, as it dictates how deep and how forcefully the venom is delivered. To understand the sheer force of this injection, we rely on the standard physics formula for pressure. Conceptually, pressure tells us how concentrated a force is over a specific area. In this equation, P stands for pressure, measured in pascals. F is the squeezing force applied by the compressor muscle, measured in newtons. A is the cross-sectional area of the tiny venom duct inside the fang, measured in square meters. If the muscle applies more force, the pressure increases. Interestingly, if the area of the duct decreases, the pressure also increases, allowing the snake to drive venom deep into dense muscle tissue. Let us apply this pressure formula to a real-world scenario. We are given a squeezing force of 15.0 newtons and a microscopic duct area of 0.03 square millimeters. We need to find the injection pressure. First, we convert the area into square meters by multiplying by 10 to the power of -6, ensuring standard units. Next, we divide the force by this converted area. The result is a massive 500,000 pascals. Physically, this incredible pressure explains how a snake instantly forces thick venom deep into its prey in a fraction of a second. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that cranial kinesis allows the snake's loosely connected skull bones to move independently, creating a brilliant folding mechanism. Second, we saw how this linked chain of bones acts as a biological lever that mathematically prioritizes blinding speed over crushing force. Finally, we calculated how powerful compressor muscles inject venom under extreme pressure. You now have a deep, profound appreciation for how chordates adapt their anatomy to survive. Great job following along with both the biology and the physics of the snake's bite.